Hello, and welcome to the DesignBase Power Flow Motor Starting Program tutorial. In this lesson, we will learn how to run a basic motor starting analysis on a network of your choice. Before you proceed with this lesson, make sure that you take the time to review the contents of the Advanced Power Flow Program tutorial coded as PF-1. Let's first review the purpose of a motor starting analysis using the Power Flow methodology. The main objective of this type of analysis is to determine the impact that a motor starting event has on the rest of the power system. To accomplish this, the DesignBase program performs three power flow runs described as follows. The first run is called before motor starting. This is basically a regular power flow calculation with the starting motor offline. It calculates the power flow conditions in the system without the effect of this motor load, and the results are the initial conditions that this motor will face upon startup. The second run is called during motor starting. This is a power flow calculation in which the starting motor is switched online and it is modeled using its corresponding starting power factor and locked rotor amps. Here we can evaluate the voltage dip throughout the system caused by the motor starting event. The last run is called after motor starting. In this power flow calculation, the motor characteristics are changed to the running power factor and load current. For example, if the motor is running at full load, the nominal values of power factor and full load amps are used. Here we can evaluate the effect of all the loads in the system, including the started motor. One last detail before we continue. This program can handle multiple motors starting in the same analysis. However, such startups are always considered to be simultaneous. For time-staggered motor starting analysis, please refer to the Advanced Transient Stability program. Now, let's begin by opening the file of interest. As always, make sure that this file contains a viable network free of modeling errors. The first step is to select the motor or motors that we wish to start. In our example, we will start motor M1, so let's go ahead and double-click on it to access the editor. Next, select the Short Circuit tab to review the electrical properties of this motor. Pay particular attention to the motor's nameplate horsepower, nominal power factor, starting power factor, and locked rotor current values. Now, let's move to the Motor Start tab and set the motor to the starting mode by toggling this button from the running to the to be started position. Next, set the motor starter type to the method of your choice. In our example, we'll start the motor across the line, so we'll select full voltage. Notice that the tap setting field reflects a value that corresponds to the method selected. In our case, 100% for full voltage. Had we chosen Y delta, for example, the tap value would have been automatically reduced to 33.33% as it corresponds to this type of hardware. If you're using a method not listed here, simply select Other as your starter type and manually enter the appropriate tap setting value. Unless you're using a solid-state starter with a specialized starting algorithm, the motor load type should be left as constant impedance. Before we exit the screen, remember that you have to repeat this process for every motor that you wish to start. Let's reset our starting method to full voltage and select OK to return to the single line diagram. To make things a little more interesting, we will run the motor starting analysis using the minimum utility fault levels. This way, we can maximize system losses for a worst-case scenario analysis. To do this, double-click on the utility symbol, select the Short Circuit tab, and move this slider to the Apply Short Circuit kVA Min position. This will use 250 MVA instead of 500 MVA as the available fault level. You should know that this process could be automated using the Scenarios function, but I'll let you handle that as an exercise. Select OK, and let's return to the main menu. Now that we have completed the preliminary steps, let's proceed to invoke the motor starting program by selecting the Advanced Motor Starting option from the Analysis menu. Alternatively, you may also select the Advanced Motor Starting icon from the Tools icon palette. The first setting is the Analysis Pick List. Here is where you can choose the different types of power flow analyses to use in your study. In our case, obviously, we'll select the Advanced Motor Starting option. The first icon gives you access to the Motor Dynamic Information interface. This is used in dynamic motor starting simulations, which will be addressed in other tutorials in the series. For now, we'll simply skip this icon. Please note that the rest of the icons are similar in function to the ones used in the Advanced Power Flow program and are explained in detail in the tutorial coded as PF-1. Please refer to this video for all the basic explanations. The next command invokes the motor starting options. Here, we define critical parameters that will control the calculation process. In the Simulation Methods section, select the Simultaneous Multi-Motor Starting Snapshots option. Let's also check the Auto Text Report to display the results right after the simulation is completed. In the Include Power Source Impedance section, we'll select the X double prime or subtransient reactance. This will cause the program to include the utility's fault impedance in the motor starting calculation. The rest of the options will remain as shown here. Please refer to tutorial PF-1 for details and explanations. Select OK to return to the main menu. Next, we'll proceed to run the analysis by pressing the Analyze icon. Once the analysis is completed and convergence has been successfully achieved, the results are shown in the Output Text Report. This document shows all the relevant information pertaining to the motor data, power source internal impedance, and calculated bus voltage results. In the Bus Voltage Results section, we can review all the calculated bus voltages before, during, and after the motor starting event. Please note that these values are shown in per unit. The voltage dip column shows the percent voltage drop that corresponds to the during condition, or load flow run number 2. Please be aware that these percentages are relative to the voltages calculated in the before condition, or load flow run number 1. The Start Method column shows which motor or motors were started during the simulation. Now, let's minimize the report screen and take another look at the single line diagram. Note that all the results are displayed based on preferences entered in the back annotation interface. Please, once again, refer to the PF-1 tutorial for more details on how to do this. A closer look at the results, however, shows what appears to be a discrepancy between the text report and the network displayed values. For example, let's take a look at the voltage drop at bus SWG2. The single line diagram clearly indicates a voltage drop of 13.29%. The text report, on the other hand, indicates a value of 12.19% for the same bus. As a matter of fact, none of the results match between the two outputs. The question is, why would that be? The answer is very simple. In the text report, the voltage dip values are measured relative to the results obtained during the first power flow run, or better known as the before motor starting analysis condition. The voltage dip values displayed on the single line diagram, on the other hand, are measured relative to system nominal values. Thank you for watching, and stay tuned for more video tutorials in this series.